Hello grade 10s, welcome to this lesson in our series on comparing physical and chemical change. Today we will investigate two types of chemical changes. Let's look at examples of these two types of chemical change that occur with a red-brown metal you should be familiar with, copper. So let's cross over to Diasha to find out more about metals.
Can you imagine life without metals? Think about it as you ride to school on the bus. Your seat has a metal frame to make your ride comfortable. The body of the bus is made mostly from painted metal. The greasy engine is fashioned out of many different shaped parts, almost all made from metal. None of the many electric circuits in the bus would work without an especially useful metal, copper. The headlights, the brake lights, the flashing indicators and the lights inside the bus are all in electric circuits made mainly out of copper. There are few other substances that are as useful to us as metals, but people haven't always used metals so extensively because only very few metals are found in the Earth's crust as pure elements. Most metals have to be extracted from compounds in which there are atoms of the metal element. Copper is one of the metals that is found in the Earth's crust in a variety of different minerals. The copper in minerals doesn't look like copper, and it has none of the useful properties of copper. Copper atoms must be extracted from or taken out of these minerals. Extracting copper atoms from minerals involves changing the minerals, and it is these changes that we will find out more about during this lesson.
In this lesson, we will describe some examples of chemical change, and you will be able to explain what is meant by decomposition and synthesis reactions. Let's cross back over to Diasha to find out more about the extraction of copper metal from its ores.
The process of changing copper minerals into copper was discovered about 6,000 years ago in the Middle East. People must have discovered how to make the change happen accidentally. Imagine brightly colored rocks like malachite and azurite finding their way into a cooking fire. In the heat of the fire, carbon from burnt wood reacted with these minerals. Imagine someone finding small pellets or beads of copper in the ash when the fire died down. People must have soon discovered that these reddish-brown pellets had amazing properties. Beating these pellets with a stone easily changed their shape. People could flatten them, bend them into whatever shape they wished, and the copper didn't shatter. The new material, copper, must have seemed quite magical because it had properties quite unlike any other available material. Later, people extracted copper from its minerals deliberately. Archaeologists have found the remains of very old settlements in many places in South Africa where copper was extracted. Near Palabora, archaeologists have found a 5-meter-long tunnel ending in a gallery that shows that people mined copper minerals about 1,200 years ago in that area. People living in these old settlements heated copper minerals in ovens made from clay, called furnaces, similar to this one.
The type of chemical change where copper is extracted from its minerals is called a decomposition reaction. It involves the breaking down of compounds into simpler substances. Let's cross over to Diasha to find out what happens when a copper compound is heated.
Let's find out what happens to copper mineral, say malachite, inside a furnace. We won't use a furnace, of course. Rather, we will investigate malachite in much the same way as a French chemist, Joseph Louis Proust, did in about 1799, heating it in a flame.
I'm going to heat some malachite in an open test tube. Watch what happens. It isn't melting, but its color is changing. It's going black. Is this black solid a new substance? Proust must have asked the same question when he heated his malachite samples. Sometimes it's impossible to tell what happens during heating. That's why Proust made measurements of the green malachite before heating and the black powder that was left over after heating. He may have got some data like this. Let's have a closer look at it. This shows that heating a sample of 10 grams of the green powder results in producing 6 grams of the black powder. So when you heat malachite, mass is lost. Let's go back to Diasha to find out why.
Thanks, John. Well, Proust heated many different samples to make sure of this discovery, but he always found that the malachite lost mass when he heated it. Look, 19 grams is less than 30 grams. Heating 100 grams of green powder forms 64 grams of black powder. This means that the black solid is a new substance. New substances form during chemical changes, so heating malachite causes it to change chemically. Since malachite loses a lot of its mass during the heating, it breaks down to form a simpler substance. This breaking down of simpler substances is called decomposition. So we say that malachite decomposes when heated. Proust knew that malachite is copper carbonate and that heating it changes it into copper oxide and a gas, carbon dioxide. The word equation that describes the decomposition of copper carbonate on heating is copper carbonate brackets S, green, becomes copper oxide brackets S, black, plus carbon dioxide brackets G. The gas, of course, escapes from the open test tube. We call an experimental setup from which matter can escape an open system. That explains why malachite loses mass on heating. So, heating malachite changes it into copper oxide. But of course, copper oxide is not copper. So another change must have taken place in the old furnace. Our ancestors used wood to heat their furnaces. We all know what happens when a wooden match burns. It goes black. This black substance is charcoal, and charcoal is carbon. And it is this charcoal that gives us the clue that we need to further investigate what happened in those early days in the blast furnace. Let's cross over to John for some more experimentation.
Right, have a look here. I've gouged a hole out of this charcoal block. I'm now going to pack the hole with some black copper oxide. Next, I'm going to use this blowpipe to direct the flame of the Bunsen burner onto the copper oxide. Watch and see what happens. Do you see the copper oxide keeps glowing even when I stop heating it? This tells us that energy is transferred out of the reactants into the air. The reaction between copper oxide and carbon is an exothermic change. Now we'll let the carbon block cool down and then have a look and see what's happened to the copper oxide. Wow! The black copper oxide seems to have disappeared. A new substance has formed, so we can definitely say that this is a chemical change. All that is in the hollow now is this red-brown pellet. It must be copper. Heating copper oxide with carbon in an open system causes it to change to copper. But what happens to the mass? Do you think it increases, decreases, or stays the same?
Isn't that fantastic? Let's look at some data to see if we can answer John's question. Look, 6 grams of copper oxide forms 5 grams of copper. 19 grams of copper oxide forms 15 grams of copper. All the samples of copper oxide lose mass when they react with carbon. The second column in this table shows the mass of 4 different samples of copper oxide before heating with carbon in a flame. The third column shows the mass of copper obtained from each of these samples after reacting with carbon. Did you predict that copper oxide loses mass when it reacts with carbon? Well, if so, you are correct. But not surprisingly, the more copper oxide you react with carbon, the more copper you get. The missing mass must once again be a gas that escapes into the air. Can you guess what the gas is? Look at the word equation again. Copper oxide changes into copper when it reacts with hot carbon. What gas do you think the oxygen and carbon react to form? That's right, carbon dioxide.
Let's recap what Diasha and John have shown us about this decomposition reaction. Green copper carbonate, which is a solid, decomposes when heated into solid black copper oxide and carbon dioxide gas. Let's look at another example of decomposition. Let's cross over to the lab. We will need some dilute hydrogen peroxide and manganese dioxide. We will place a small amount of hydrogen peroxide in the conical flask. We will fill a test tube with water to collect the gas formed by the downward displacement of matter. The collecting tube is placed into the test tube. Now we will add a small amount of manganese dioxide to the conical flask. Place the stopper in the mouth of the flask and insert the glass tubing to the rubber tube. We gently heat the hydrogen peroxide over the Bunsen burner. Note the gas bubbles that are coming out of the end of the rubber tube into the test tube. We can test if the gas in the test tube is oxygen. If we take a glowing match and place it into the test tube, the match bursts into flames, so the gas is oxygen. Let's take a look at this reaction by looking at what happens to the atoms in the hydrogen peroxide as it decomposes. Microscopically, the hydrogen peroxide decomposes into water and oxygen. The manganese dioxide is just used as a catalyst to speed up the reaction. Let's take a closer look at this reaction. Note that the two hydrogen peroxide molecules decompose and form 2 molecules of water and 1 molecule of oxygen, so the number of molecules has not been conserved. Note that the number of each type of atom is the same, but they have been rearranged, so the atoms are conserved. Let's cross over to Diasha to find out what happens when copper metal is heated.
Now, what happens when we heat copper in the air? The copper is in an open system. Look at the color of the copper foil before I heat it. Do you see its unmistakable red-brown shiny color? Watch how its color changes in the flame. It goes black. This means a new substance has formed. This must be a chemical change. Copper cannot decompose into simpler substances, for it is an element. Rather, heating copper in air makes it combine with the oxygen in the air. The word equation representing this chemical change is copper plus oxygen gives copper oxide. Oxygen, like all matter, has mass, and so combining with oxygen must increase the mass of copper. We call this a synthesis reaction.
A synthesis reaction involves the combining of substances into more complex substances. Let's look at one more example of a synthesis reaction. This type of synthesis reaction could one day be used to power the car you drive. This is a Honda FCX Clarity, introduced in 2008. This is an example of a hydrogen vehicle. This car has a hydrogen fuel cell. Hydrogen gas reacts with oxygen to power electric motors. Here is a block diagram of a fuel cell. In a fuel cell, hydrogen gas is used as the fuel. The hydrogen reacts with oxygen gas. Water is produced as a product of this reaction. Microscopically, we can see the 2 hydrogen molecules react with 1 oxygen molecule and form 2 water molecules. Note that the number of molecules is not conserved. We started with 3 and land up with 2 in the product. But the number of each type of atom is the same. They have just been rearranged. One of the advantages of a fuel cell is that it does not produce emissions such as carbon dioxide. However, the cost of manufacturing these fuel cells is still high. In this lesson, we have identified 2 types of chemical change: synthesis reactions, in which simpler substances combine to form more complex substances, and decomposition reactions, in which substances break down into simpler ones. You can practice identifying whether a chemical change is a decomposition or synthesis reaction in the task video, and visit the Mindset website www.mindset.co.za/learn. Join us next time when we will look at an important discovery. Until then, goodbye.